So today we will talk about the basic of data science in Python, which is the NumPy arrays. So far we have seen that in Python we have the, the, the most used data type, one of the most used data types is the list. So list is very flexible. It can grow dynamically. It can be also compactified in the sense that you can remove elements from anywhere from the list, not only from the beginning, but also you can actually remove elements in the middle or anywhere, any position you can. So you essentially have a very powerful tool where the array, all array and list are the same in this context, can grow dynamically. It can keep track of the size as it grows, or it goes down, the size goes down when you remove elements and so on. So but for that you pay a huge price also. That means the Python has to keep provision for all these operations, that you can add one element from the back or from the beginning or any point. And if you really think about it, you will understand why these are absolutely costly operations. So I will not go into much detail. I'll just verbally tell you one such example. Let us say Python, you have a list. Okay, so you start with an empty list and you keep on adding elements. Okay, so when you declare a list by creating an empty list, it may not mean, although I don't know the exact answer in C++, I can tell you. So in C++, for example, some of you know C++. So the equivalent of list in C++ is like a vector. Okay, also we have list in C++. Let us say it's a vector. When I declare a vector, then without telling me, C++ will reserve actually 20 elements, okay, of the data type that you are specifying while you are declaring the vector. Because in C++ you have to also immediately declare the type of data that the vector as a container will contain. Okay, so it will keep provision for 20 such elements. So now when you start appending to the C++ vector one element after the other, what will happen is that up to 20, you don't need to expand memory at all, because the initial allocation was for 20 elements. Now, when you are adding the 21st element, then what it has to do is a very costly operation. It has to grow the array now, the underlying array, because vector is also somehow implemented based on an array. And because this is a dynamic expansion, dynamic array, then what you have to do, you have to now create another array with size 40. Okay, so you have a different array. Okay, a new independent array with size 40. Then what you do is you copy from the original array 20 elements as the first 20 elements of the new array, and then you delete the original array. So you see the operations, how costly that could be. The same thing happens in Python also. Even more complex things happen when you try to insert an element in the middle of an array, because now you are actually not only growing your array, you are also making space for a new element in the middle of an array. So that will be very difficult. So what then C++, I think it is the same in Python, although I don't know the detail. In C++, what if you were to do that, what it will do is that it will again create another array. Okay, then it will actually copy some elements from the original array as the first few elements of the new array. Then the position where you want to insert a new element will be inserted, and then from the original array the rest of the elements will be copied and the original array will be deleted. So you can see that this expansion, contraction, adding.
Subir, I
Yes.
don't see the slides changing. I don't know about
No,
others.
I am not actually changing the slides at all
Oh,
because
okay, okay.
I don't have slides yet. So I'm just giving the concept
Okay, okay, okay,
about the
fine.
list. Why lists are very flexible, but at the same time, why lists are very costly elements in any programming language. So also C++, C, etc. So wherever possible, you would avoid that. That means it will be good. For example, in data science, nobody actually really deals with dynamic thing. I mean, for example, machine learning, you sort of know if you have a network, you know the number of layers in each layer, the number of nodes, etc. You predefine. Okay, so you know how many elements I am dealing with. I will not really use a list there because list is a totally misfit there. Okay, so that the Python developers, when they knew from the very beginning that that list is not the right kind of container if I want to do mathematical operations. Okay, so with that introduction, I think you have, I mean, more or less understood why dynamic memory allocation is not a very good idea when you don't really need them. So what Python now does for NumPy, so the people who developed NumPy, they understood that the Python list is really useless when I am dealing with large amount of data. That means so the size of the list is absolutely big, like of the order of 10,000, 100,000 or million and so on. It will be almost impossible to work with them because a list, there is no stripped list. That means if you are using a list, the list will have all those properties and Python will have to support. Even if you don't operate, Python will have to support all those properties. So the code base will be very big and it will be very slow when you operate. So what they did is that they went back to real C with fixed size array. So instead of, so you should know the size of the array well in advance before you actually create the array. If you do that, then you don't have to keep provision for dynamically growing the array and so on. So you know that is fixed size. That's the first point. And then the second one is also quite important, and this I think will answer one of the questions that was asked, that if I know the data type, if I know the data type or if I specify the data type, whether this can optimize my performance. And the answer was that yes, it does, but I cannot. At that point, I did not have an example to show, but now I have. So the second point of the list is that the list doesn't really care about what kind of data type you are going to put in there. That is why you don't really specify the data type. So the NumPy developers also realize that that is a drawback. So what you can do is that you can specify both. You can say that my array will be fixed size, and from the very beginning, I will know the data type which I am going to put in that array. So essentially, it's C. It's simply a C array. So you take, so the NumPy, I mean, if I put in a very simplified word, if I put in a very simplified word, the NumPy, now I am actually moving the slides. I hope now you can see it. Okay, so NumPy is a C extension module for array-oriented computing. And essentially, you take a C array and you uh, create an interface which looks like Python. But at the end of the day, the operations are very close to C. That means you cannot really expect more performance than what you get with NumPy. So essentially, although NumPy is a Python module, it has a very close bonding with C, very close. That means whatever you do from NumPy, actually, you directly go to C. So it is absolutely performing compared to the list. I can show you at least one or two examples where you will see that with a large array, the list doesn't even work. It might take you hundreds of seconds, while the NumPy version of the same thing will be done in a few milliseconds, even less than that. This one, I have one example of that. So on top of that, because C array is good, but as soon as you go to multidimensional C array, it doesn't remain that flexible. So Python has to do a lot more work so that a matrix operation looks very natural. With normal C, it would not look very natural. So you have to write a lot of extension modules on top of a C array. And that is why that is what Python, the NumPy developers have done. They have optimized it very well. They also actually provide you a lot of compiled function inside NumPy. That means the compiled function means they are not only written in C. When you call them, the corresponding C is immediately called. This way they are compiled. So all the parameters that you pass to the Python functions, actually they have one-to-one correspondence in the C world. So they are immediately called. You don't have to, there are no other extra code or extra steps in between, so that you can extract the highest level of performance. So this is very important, that you want to do data science. We know that we want to churn a large amount of data, and performance is the most important thing. So even if I have to give up or sacrifice some flexibility, I'm fine. But fortunately, it was found that you are not actually sacrificing a lot of flexibility, because of the fact that in the world of data science, you are not really dealing most of the times, and maybe there are some occasions you do, most of the times you are not dealing with dynamic dynamic size of an array. And also you are mostly, because it's data science, it's mostly mathematical operations, you are mostly dealing with fractional numbers, decimal numbers. You are not dealing with really big objects and like that. So both of them tell you that you don't really need the list. You really need a stripped array list, which is the NumPy array. So this is already something which is there. So the important point is that the performance of the NumPy array is similar to C, exactly similar to C. And as I said, that it was developed by experts and optimized over the years. And also one of the very high level concept of NumPy is that you have pre-compiled mathematical and numerical functions for performance. So this, I don't want to really go into detail. I am not expert in that. All I understand is that when I say pre-compiled, that means you can call those mathematical functions, and they will be there. You pass Python parameters, they will be immediately converted to C parameters without much code in between, and they will be called in the C world, and you get the result. So that way, they are directly coupled to the coupled as C. Although they are Python functions to U, they are actually C functions to NumPy. Okay, so that way you get like best of both worlds. That means you still spend a lot of effort to Pythonize the NumPy library. And it took them some time to Pythonize the NumPy library so that it still looks like Python. But I know that it's not Python. It's simply C. It's just a wrapper on a C array, either one dimension or multi-dimensional C array, depending on the case. And I have a lot of wrapper code. And if I remember correctly, there are in NumPy, there are more than I think 500 functions. Okay, I don't think we need all such facilities. We will only work with a few of them, but because it's a, and also the other important point is that the NumPy is so famous. NumPy has actually inspired similar array in almost every language. Okay, for example, C++ also has array like C array, and we know that C array has a lot of handicap, lot of limitations. Then how does C++ do the machine learning? So they have another array which is called eigen, which is not exactly similar to NumPy, because they probably were started at the same time with slightly different philosophy. Of course, because it's C++, it is more performant than NumPy. Eigen, and all the machine learning libraries like TensorFlow and others, which are based on C++, are based on eigen elements. And nowadays, there is also in C++ another library. So if any of you are interested in using C++, but following the NumPy kind of strategy, then there is another one is called xtensor. Okay, xtensor. So I'm just giving you the names. They are not very important. The important point is that NumPy has inspired similar strategy in other languages like C++, like Julia, etc., etc. Okay, so this is now technically okay. Before I go, we already said that NumPy is the basis for data science. So if you look at the right hand image, you see that you have Python, let us say core Python, and NumPy sits on top of core Python. Although it's Python is also written in C, and NumPy is not written in Python. NumPy is directly written in C. So in principle, NumPy could be at the same level as Python in terms of its implementation. Okay, and the other all other elements which are needed for data sciences are directly based on NumPy, like the SciPy, the pandas, matplotlib. Everybody they have their own elements also, but they use NumPy array as the basis. Okay, so for anything that you do in data science, I think you have to learn NumPy. Now the initial implementation of NumPy assumed that there is only one CPU core, but we know that now there are not only one CPU core, there are multi-core, and also there are GPUs. So there are also revisions and new implementation of the NumPy where you don't change the interface. The interface looks the same. Maybe the name of the library changes. For example, for NumPy, there could be something called a CUPy, which is for the CUDA related. I mean, for the GPU programming. But the interface remains the same when you use CUPy instead of NumPy. Actually, that is GPU compatible. So if you have GPUs, then it can directly, without you knowing what is happening, the GPUs will be used, all the GPU cores will be used while doing the mathematical operation. So that is another very, very important development in the NumPy world, which you should keep in mind. So when you use machine learning, when you do training of your network, and you know that I have GPUs on my the machine where I am working, then probably you will not use the classic NumPy, but you will use the GPU enabled version of NumPy. But then when you import the module, you will say that you import the GPU enabled NumPy as NP, and your code will not change because the only a single line will change. So anyhow, we'll come to that. Okay, now more technically, why I have already discussed a little bit. I will tell you the list versus NumPy array, because I think the concept is important. The rest, after the concept is done, the rest will be practice session, where I will show you some in the interactive session on the notebook, some of the ways that the NumPy arrays are used. And then I have all the slides where there are a lot of details which you can follow. I also have a lot of examples which I will not be able to cover here, but I will share with you so that you can practice. So if somebody tells you how does a Python list should look like technically, then you can look at this picture. So in a Python list will have some kind of C interface, okay, because Python list, as I said, is also based on C arrays. There is nothing that Python so Python takes the original C array, then writes a lot of extra software in order to make sure that it looks like a Python list. Okay, on top of that, because of the fact that Python list can contain any kind of data, so each element should also be a complex object, may be a complex object. It could be an integer, which is a simple object, and it could be a histogram also, in which case it's a complex object. So Python has to keep provision for both. So if you have to keep provision for both, actually you have to give the complex, the higher part. So what happens is the following: if you have a Python list, then you have some header. Okay, you have some header which you can ignore for the time being. We know because Python list already knows. I mean, if you apply the len function on a Python list, you get the length of the list. So in principle, somewhere the length will be saved, so that the dynamical length will be saved, and whenever you query that, it will return you that length. And then you will have the items in the list. Okay, so this is the, if you just simply look at superficially to the Python list, you see these two elements, length and the items, and of course there are some headers. And this length will change dynamically as you add or remove items. Okay, so this is what I have already said. For each item now could be a complex thing, so they will have their own memory addresses. Okay, which we discussed yesterday. With the id function, you can check that each of the elements of a Python list will have different ids. That means they also have their independent existence, okay, in the memory space. That means if I take one of the items, then this one, because it's a complex object, this will also have some structure. Again, that item will have some C implementation. So it will have some header, it will have some other data. Okay, so that way, that data could be very complex, that data could be integer, very simple, and so on. But you have to keep provision for that. So if you really look at the Python list structure, you see that it's very complex, and not only very complex, you are using a lot of variables in order to represent a Python list. That means you are actually consuming a lot of memory also. Plus you are keeping provision for dynamicity, so you are also losing a lot of performance. Okay, so the details of what I'm showing or what I'm discussing are given here in this link. If you want, if you're curious, you can check that. Now the NumPy array is simpler. NumPy array doesn't really keep provision for all these things, because you have stripped all the power of the list. You say that it has to be a fixed array, fixed size array. So the length will not change dynamically. And you probably, the dimension part, so not the dimension, the length part you specify in the beginning. Okay, then it continues to stay like that. And your data also, the items doesn't have to be very, very complex, because they are only a single data type. So either integer or fractional number, floating point number. If you tell me whether NumPy can take an object, yes, it should. You should be able to use objects also, but usually objects like strings, you don't really care about very complex object in NumPy. Okay, you mostly work with the decimal numbers. Okay, so here you can see that you have the object, the Py object header, of course. And for any object, there will be a header which actually connects you to the C world. Then you have the data. Here it is integer data of fixed size, so you have the data. Then you have the dimension. Okay, because with the NumPy array, you may have dimension 1, 2, 3, etc. Okay, you have vector or matrices, etc. And there is another one which is called a stride, with a definition that if you want to go to the next element, how much you have to skip in between. Okay, so in the case of integer, is very easy. It's like simple C array. Okay, integer array. So here you can see that it is not very much different from a very bare minimum C array, where you have C array. When I say C array, I didn't mean only a single dimension. It could be multiple dimension also, and it's very close to that. So it serves two purposes. You have fixed size, and because of that, and because of the fact that your data type is also fixed, that means a NumPy array cannot take in the array cannot contain items of different data type. So all this tells you that it is at the same time both memory and CPU efficient. Okay, so this is your NumPy array. Okay, more towards concept. So NumPy features again, and now I will repeat that this means you have smaller memory footprint when you work with NumPy arrays. If you have smaller memory footprint, that means you can work with a much larger data set given the same amount of memory. So if you want to work with list and with NumPy, if you can check the sizes of a NumPy object for the same kind of data container, data against the list object, you will see that the NumPy object has a smaller size. That means you can deal with more data simultaneously. So, and NumPy, as I already said, they had to make a lot of effort. Okay, and I think at the end of the day, they are successful to make it look like Python code. Okay, although it's, I told you there's almost C, but still with the kind of wrapper code, it looks like Python. Okay, because we are talking about data science, we are talking about algebraic operation. Okay, so I discussed yesterday about operator overloading. So NumPy also does the operator overloading, and that is one of its main features. Okay, we'll see that. Okay, then there are two more very important concepts of NumPy. One is called vectorization, and the other is called broadcasting. Okay, these also we have to understand. Okay, this I will give a very simple example of vectorization, and broadcasting is a definition, and it's some kind of flexibility in the library. So NumPy, as I said, NumPy is the basis of everything in Python, all the data science, and NumPy has got all the features. So with NumPy, basic NumPy library itself, you can achieve a lot. But of course, we know that NumPy is just a tiny part of the whole data science. So if we start from somewhere, we can say that NumPy is an alternative for lists. That's the first thing. It supports matrix operation. That means there will be, I say there are like 500 functions in NumPy. So it will support matrix operations. You can copy, and also without copying, you can view arrays, you can do arithmetic operations, you can do statistical operations, you will do broadcasting, you will do other mathematical operations. You can also, in NumPy, you can do searching, you can do sorting, counting, you can even do bitwise operations with NumPy arrays, you can do okay, so these are you can do linear algebra. Okay, so NumPy is a world by itself. Okay, so Python, if you now, yesterday I said, now we'll move away from Python. Okay, so in some sense that is true. All the examples that you will see that will hardly have a lot of basic Python. Okay. Now the very important concept of vectorization. Okay, what is vectorization, why it is so important, and more importantly, I told you that for loops are prohibited in Python, and now you will understand why for loops are prohibited in Python. Okay, you should not do, whenever you do something in data science, you should forget about for loop and using your data in a for loop. Okay? So what is vectorization? Vectorization is a hardware feature. That means the modern CPUs are capable of executing more than one instruction set at a time. It is called SIMD, single instruction multiple data. That means you give one instruction, but multiple data can be used. Okay, and this is, as I said, it's a feature of the architecture of the CPU. So this capability will change from one CPU to the other, but it has nothing to do with software. It's a hardware feature. Because it's a hardware feature, it sits very close to the hardware. Python cannot access this feature at all, because Python world doesn't really connect to the hardware. It has to go through C. So now what is that? If I put very simply a C example, we can understand what vectorization means. So you write, for example, if I have three arrays, okay, where A and B are input arrays and C is the output array. And let us assume for simplicity that the n, the array size is 16. Okay, array size 16. I want to sum up A and B, and I get C. Somehow, I mean, here is an incomplete code. Let us say somehow A and B are already filled. They are of the same size. So I loop over n. I say C of I equals to A of I and B of I. I think this absolutely clear to everybody. This will work in Python. This will work in any language. Now, if your architecture, your CPU, now with any modern CPU, I think this is the case, you don't really bother about any detail of vectorization. You write your own code, and your compiler or maybe some other part, some more deeper part, will convert this code into the code which follows, where I am assuming that your CPU is capable of executing 4 such independent SIMD instructions. So you can see that you immediately gain a factor of 4 here, because your loop is unrolled into this loop. You have a loop where each time you are accessing only one element, but here you can see that each time you are accessing 4 elements. So this is the simple concept of vectorization. In C, in C++, in Julia, languages which actually have this capability very close to the hardware. I don't know about Java, whether Java can do it. At least C, C++, and Julia, I know that they have the vectorization already inbuilt. So what does that tell you? That tells you that these languages, probably also Fortran, I'm pretty sure the modern Fortran will also have the vectorization, because we know that it is still the fastest executing language. Okay, so this tells me that I can still use for loops. I don't have to abandon for loops in languages like C, C++, and Julia. I can do that. But if you now think about a Python code, equivalent Python code in this case, and you know that you will write Python, this client code part, this will not be vectorized, because you are doing the loop in Python, in the Python world. But Python world doesn't support vectorization, because it cannot directly connect to the SIMD part. It cannot. It has to. You have to do something else. So what is that something else? You will have to avoid or abandon the for loop, and instead you will have to pass your data to a C function. As soon as you pass your data to a C function, C has the capability of vectorization, so vectorization can be done. So if not anything else, and nowadays, if I what I read is that nowadays we have 4 SIMD instruction as the default for modern CPUs. But depending on the development of the CPUs, this might grow. Maybe someday we might have another factor of 2 and so on. So this will be already inbuilt. You don't have to change your code in order to achieve that factor of 2, etc., etc. Okay, this will always be there as the architecture changes. Okay, so that's why, if not anything else, you have to abandon Python loop, because the Python loop cannot get the vectorization. Without, I mean, instead of Python loop, you have to really call some function which directly passes your data to the C world. So now the question is, which one is more advantageous? That means you do some work in the Python world, or you send it to a function where you send the whole data to the C world, because there are two contradicting concepts here. One is that you lose vectorization if you work in the Python world. The other one is that if you pass your data from the Python world to the C world, you also need to pass the data from the Python world to the C world, and it takes some time. Okay, but it was found that with the pointer technology, with the pointer, Python can somehow manage to instruct C about, without really copying the data, from the Python world to the C world. It can tell C where the data is stored, and C, of course, C is the basis of everything. C can directly access that data through the pointer. Okay, so if C can do that, C can now loop over can have a very simple loop where the vectorization is inbuilt, and C can gain that factor of 4 immediately for you. Okay, so that is vectorization. That is very important. And NumPy, I told you that NumPy is very close to C. That means NumPy is vectorized. In NumPy, you will never see, when you deal with NumPy arrays, you will never go through a for loop at all. You will only call a function. Okay. Now, without further ado, I will now show you one example of the performance. Okay. So NumPy is my module. Are you following, by the way? Because this is a difficult concept, and if you have questions, you can ask me here. I am not a big expert. I will try to answer this, but these are very basic things. Okay, so you should understand this before proceeding. So if you have any, I don't know whether there's any chat box, anything. If you have any questions, you can ask me. Otherwise, I'll start with the. I have already talked enough. I'll start with the example. So Python performance. So NumPy, I think even if you are new, all of you have heard about the NumPy module, and we know now NumPy is, although it's not a long name, I can still, by you following the convention, I can shorten it to NP. So what I say is import NumPy as NP. Okay. Now inside the NumPy module, this is the module. You have many facilities. One of them is that I can create random numbers. Okay, so that's what I'm doing here. I have n equals to 1 million, and I want to create two random numbers, a and b. Random number, not random numbers. I will create NumPy array. Okay, array which is 1 to 100. So the value will be distributed from 1 to 100, and the number will be n. That means I want to create an array of size 1 million, which is A, and also B of the same size, and the values of the array will be distributed from 1 to 100. So I have done that. Now I will start executing it. Let us get the sum of any of the arrays. Okay, using a for loop and see what happens, how much time Python takes. And if I don't do that, if I call a vectorized version, that means a function where I will pass the array, the NumPy array now, array, and NumPy will take care of it, how much time it takes. And I will see that there is a huge difference. So let's start with that. And that will convince you why you should avoid, and why when you work with NumPy array, if you are looping over a big chunk of data, you never do a for loop. Okay, so import NumPy array, then you create your array. So if you are curious, I can print a, and you see that these are the values. Okay, and these three dots means it is not printing all the numbers. Then I define this function, and this function should be very familiar to you, that you want to sum the argument where the argument is an array. Okay, not a number. So s equals to 0, then I loop over the array. My s is s plus the number. Okay, and then I return s. This I don't have to really. Now on the notebook for Python, you have a macro called timeIt. timeIt I think is a module in Python which will be automatically invoked. So it has the simplicity that you don't have to do it by yourselves. That means in principle there are many time modules in Python also. You can add the time module in your code, and then you start, you say start, you say, and then you execute your code, and you say stop, and you say stop minus start is the time that it takes, and so on. Instead of doing that, you can simply use the timeIt in a particular way. So because it's like a macro, the particular way is that you put 2% and timeIt, and then you call it. Okay, so you call it, and you see that now you're stuck because it is looping over a 1 million element of A, and it is trying to do the sum. So it did. Okay, it did. And in order to do it, 1 million element to sum up, it takes about 169 milliseconds. 169 milliseconds. Okay. Now, instead of doing this, I want to use the NumPy way. So we know that in the NumPy way, I will use a function. Okay, I will use a function or method if you want method, and I will pass the array to the function, or I will execute one object method. So that is the object method, which is a dot sum. Okay, a dot sum will return you the sum of the elements of the NumPy array. And let us execute this. It is still stuck, but it is stuck with time it, or it is stuck with, so there is some catch. As I told you, you saw that it was also stuck for some time, but that was to actually pass the data, the instruction about the data to the C world. But the computation is much faster in the C world. You can check that. Now from 169 millisecond on this machine, it has gone down to 1.14 millisecond. Okay, so a factor of 100, even more than 100 gain in speed for the same thing. So I think this convinces you without beyond any doubt that I should actually this one, this value, if I run it again, let's say sometime I got it in microsecond also, which will be more impressive, but I don't find microsecond now. It's no, because of other, because this is a single machine and I have other things running. Okay, I have the Zoom and I have other stuff, so probably it is sharing some CPU time with other. So it's not a powerful machine, the desktop. If you do it on your laptop, this simple thing, okay, then you will see that it is also very impressive, like it's in the microsecond level. Okay, so this is fine. You are gaining a factor of more than a factor of 100. But is it a realistic gain? You will ask. So if it's a realistic gain, then we know that Python could be very close to C in terms of speed because of this gain. And in this case, indeed, in this case, indeed, it is as fast as C. If I could show you in C, I would not really gain on this machine much. I mean, probably C will be faster by 10%, 15, 20%, but that nobody really cares about because Python is way more flexible than C. So if I could gain this and still have a Pythonic way of working, I would accept that. But let us look at the next one. Let us look at the next one. I will not add the array now with all elements. Let us say I will only add the odd elements. So if I have to add only the odd elements, then I have to use some logic. So let us write another function. Okay, let us write another function. So the another function I call def is the function sum underscore odd. And how do you get the sum underscore odd? Again, because you have a logic, you will not really do it by hand. You could also start your own for loop, and within the for loop, you could have another NumPy array with some fixed size, data type is fixed, etc. You could do that. Okay, only the odd order, or you don't even need another array. You just say if the element is odd, then you do the sum. If the element is not odd, you skip it. But we know that looping is already very slow. If I add inside the loop another logic, it will be even slower. So I don't do that. I directly go to the NumPy way, and in NumPy there is a very high level expression which will return you another NumPy array, okay, where you only have the odd elements, so that you don't need the for loop. Now really be very careful that I want to do any looping that I have to do in the C world, and I may have to sacrifice some clarity, etc., but I will do that because the performance is important, and I will get done all the looping in the C world, and only give some instruction on the Python world. So if you really look at the implementation of this function, you see that I have a function which directly comes from the module. It is not a method of an object. It's a function which called where. So where, what do? You pass the x as the input array. Okay, forget about the last one. I don't even remember because it's probably and you give the logic here. The logic is very simple. If x the modulus of 2 is not equals to 0, then you take that element and you add to another numpy array. So you only collect the odd elements and create a numpy array, and once you have a new numpy array with half the size, you return me the sum of that array. That's what I have done. You see that no loop anywhere. No, you don't see any loop anywhere. Okay, so the looping part, which is the slowest part, is avoided. But does that mean that I have the same kind of performance like here? Let's see, like a dot sum, because this one should have similar performance to this, but this line will be much slower, as we will see now, or it is already there. Okay, so this line is much slower. So I enter it, then I run it. You see that instead of 1.16 millisecond, now I am taking 21 millisecond, which is much better than 169 millisecond for just for a bare sum. Okay, but still I am giving away 15, 16 times. So this line actually is very, very costly. Okay, the sum is so if you don't have any logic, if you don't have any logic, you can simply pass your data to the C world and get the result. It's blazing fast. It's as fast as C. But if you have to give a logic, that logic you really have to prepare in the Python world, not in the C world. So after you have prepared the logic in the Python world, then you pass it to the C world, and then C does the work. Of course, in order to even C, if you have a for loop, it will take some time. So, but that time, if I would have done it directly in C, probably it would be faster. But because you are calling a NumPy function, this preparation of the data which you will send it to the C world. I don't know I don't really care too much here, but all I want to mean that as long as you don't have any logic, you can directly use the the NumPy functions. Okay, you're passing the data from your Python world to the C world. It is absolutely the same performance as C. But when you have to do some work which you have to do on the Python world and using some logic, then you are again losing some performance. So this you have to be careful. You cannot avoid that. So you will never say that NumPy is as fast as C. Okay, because as soon as you add the logic, you already lose some of the performances. Fine, this is fine. Now let us take another example which is close to what you will do in the machine learning world. So let us say A, B, and C. Okay, A, B, and C are now I am creating three NumPy arrays. These are random numbers once again, but this random number are slightly different than the one because those are integer values. Now I have decimal number, the floating point values also, but the size is the same. Okay, so I can create that ABC. Then I will never execute it. I can execute it. Now what you do is that you have another function where you are using loop, etc., etc., and in that loop what you are doing is that you are multiplying x and y and you are adding z. Okay, it's like in the machine learning world, you have the weight and you multiply that is an array, and it could be a matrix also, and you multiply with the input value plus you add the bias. Okay, which is also a vector. So this is the same. So this is used in many places, almost everywhere in the machine learning world. And you can see that what I'm doing is that I am looping over the numbers, then I am calculating this result, and I'm returning. I'm doing a sum and I'm returning. Okay, so I call it something. It doesn't really matter. So if I run it, and I have already shown you, that's what I ran earlier, that it takes 622 milliseconds. Okay, it's close to a second. It's absolutely slow. So instead of doing that, instead of doing that, now you can once again use the NumPy features. Now the vectorization comes. The NumPy, as I say, NumPy has vectorization, broadcasting, and also operator overloading. So this one, this line, if I really look at it from the algebraic sense, then I would say that x into y plus z, not x the element, ith element, and so on. So Python has actually done that. The NumPy has actually done that. If you have NumPy arrays, you can just name the NumPy arrays to do such operations. And if they are arrays, NumPy will take care of the fact that element-wise computation is done. So that also makes your code very, very clear. So the second, the next version is again the same thing. You can see that now I am writing this. S equals to x into y plus z, and I know that x is an array. I mean a NumPy array. Y is a NumPy array of random numbers. Z is also a NumPy array. So if I do x and y, there will be element-wise multiplication, which I did in the in this example, and then it will be z. That element of z will be added. So NumPy will take care of that. That the zero element of x into zero element of y plus zero element of z. Similarly for 1, 2, etc. Now, because you are doing it in the on the C side, okay, this thing NumPy will directly pass it to C. You can see that vectorization is now inbuilt. So four instructions will be executed at the time. So you already gain a factor of 4, plus you are not doing anything in the Python world, you are doing it in the C world. So all that you need will also all the speed will be theirs. Okay, so the full C in full swing uh, will be there to help fill NumPy. So this will be very fast. Okay, this one will be very fast. And then what you are doing is that you are saying that if, for example, here I was saying if s is this was t, if t is greater than 0, then only add. I don't know if this is somehow negative, I don't want to add. But this is your logic. This logic is not very important, but there is a logic. Okay, that also slows down your whole thing, because you are checking with the if statement. Not only you are in a loop, you also have for each element of the loop you have an if statement. And we saw earlier example that the if statement, even in the for NumPy, actually causes you some trouble. So if this one will be very fast, if I only look at the timing, this one will be very fast. But this one, when you look at np where means what? That when s is equals to 0, then you take the new array. Only those elements of the new array where s is greater than 0, that means s0, s1, etc. are 0. Again, the vectorization part is there. Then you so you create a new NumPy array and you return the sum of that NumPy array. Okay, so if you look at it, and so as I said, the loop part, the Python loop part was abysmally slow, 620 seconds. Now let us see what happens to this. So now I can now execute it, and you see that now it takes about 16 milliseconds. Okay, so instead of 622 millisecond, the new version where you do everything using NumPy and also taking advantage of vectorization and so on, you gain a huge factor. Okay, so this is NumPy for you, that you can forget about list. You will now forget about list in the data science, and unless you have very small things to do where you will not really see the differences. You will only have NumPy arrays, because NumPy array will have all the facilities. And not only that, with the NumPy array, you will not use any Python loop. You will only use the vectorized calls which are there in NumPy, and that is why there are many functionalities in NumPy. Questions?
Sir, what is this run number and loop number?
Here, you mean?
Yes, sir. Yes, sir.
Okay, so I have to check that. So essentially what you do, you actually run it many times. in order to have a stable result. You see that here I say mean plus STD, because if you need the STD, you cannot just run the standard deviation. You cannot just run once and give the standard deviation. Okay, so it says that you run it. You have some data, okay, and you want to time it. So in order to have a robust and reliable timing, you cannot just execute it once and give the timing. So what you do is you run it many times. Okay, you run it many times and you have an average value of the timing. So that's what it says, that you use 10 loops each. Okay, and you use 7 runs. So that this could be that you may have like 70 times, you may have run it 70 times and then give me a number, which is more reliable than if I only, like in the case, in the real case, of course you will not time it. So if I move the time it, if I move the time it here, and it will not show me anything, it will not show me anything, it will only show me the result, but you can see that it's slightly faster. But here when you add time it, actually the time it part takes a lot of time, because it is really giving you a reliable time. So it cannot simply execute the code, it will execute the code many times, and for each execution it will collect the time, and if it executes it 7 times, it will collect sum up all the times and divide by 7 in order to give you the average timing. And also from that average, it will also calculate the standard deviation, so that you have a reliable uh, estimate of what kind of timing you can expect. Does
And
that
sir,
answer?
yes, sir. And sir, in np.where you said that the if condition is implemented in Python. So why not implement the if condition in C? I mean, then we have the faster results, right?
You mean here?
Yes, sir.
No, I did not say that the if condition is implemented in Python. I simply say that here, because there is a where, of course, if you want to implement the if condition in Python, that means you are doing a loop. Okay, so then you are undone. So it is not really implemented in Python, on the Python world. What I am saying is that if you really, if you really send some algorithm to C, okay, which is this one, is greater than 0, and you see that in order, so sending s is something, sending s, which is, sending, for example, any array, sending any array to the C world is something, but sending an algorithm to the C world is not that trivial. That means, because it's this one, for example, this one, how do you tell C that I am sending something like this? So there must be some more code, which I don't know, which I don't know exactly, some more code which you have to pass to the C world in order to say that now I am sending a is greater than 0. You understand the point? So for
Yes,
example,
sir.
if I were to send only s, okay, and if I have to send s equals to 0, so either if somebody would tell me, that you send it like this, that as a string, okay, you don't send the data, you just send a string to the C world, and from the string, now the C world will find out what you actually meant. Okay, then it will find the data and it will loop over, and then it will execute the if statement. That would be a different thing, but I don't think that will be with a string based thing, that will not be very performant. So you are actually sending the instruction as code, some code. So at this point, what I meant essentially, as I said, I don't have the technical. So what I meant is that here Python will have to generate some code, so it cannot directly call C. That's what I mean. It has to generate on the fly some code, few lines of code, and all those lines of code will have to find their corresponding C functionalities, and that will actually go to the computation the C function, which will compute the same thing. So essentially, in between a Python and the C world, NumPy like computation, you will have some more code which has to be executed. That's what I mean. But I am not telling you exactly what that is, okay? Because I don't know myself. But there are some extra code, because if I as I said, if I passed only something like x, actually x is just the array reference. So C will take that array reference and it will convert into a pointer, and from the memory space it will try to see what actually this pointer points to. As soon as it will find that it points to an array, it will compute. But when you do this, you cannot uh, this one cannot directly go to the C world, because you are seeing s greater than 0. So the logic first has to be computed on the Python side, and Python doesn't want to do the loop. So instead of doing the loop, it will generate on the fly some code which will connect to the C world. That's what I meant.
Okay, sir.
Okay, so I think if you don't have any other questions, let me see. There it looks like there are some messages. Okay, it is. Can you please show the value of A and B and C one more time? I think I made a mistake. So which one are you referring to? Let's go there.
Sir, the last example.
ABC. Okay, last. This one.
Okay, thank you, sir.
Okay, so I think now we are all convinced that NumPy is a very powerful tool. NumPy is a very powerful tool in the Python world, and there is no doubt that it has inspired the same kind of strategy in many other languages. Okay, some languages don't need it. For example, I myself am a proud user of for loops. Okay, so I would rather use C++ than Python, and use the for loop, because I know that the compiler is there to do the optimization. Okay, similarly, Julia also proudly uses the for loop, and if you really take Julia and time it, I also have some example, but it's not the lecture of Julia. I can see that even Julia, for example, beats NumPy. Okay, the NumPy way. Okay, when it comes to Python calling directly NumPy like a dot sum, it is as fast as C. So that means nobody can beat it. But as soon as you put where, that means some logic, then NumPy also doesn't shine that much, because you lose a factor of 15 we saw there. But in that case, even with a for loop, Julia will not lose a factor of 15. It will lose a factor of a factor of 2. So that way, so this you have to keep in mind when I don't know whether you really need to learn all these things, but because this is a very basic of Python, when you start with NumPy, you know that NumPy is very performant. But as you add more logic in your code, which is what you will do realistically, even if so, you will never use for loop, that's for sure. Even if you use only NumPy facilities, as you add more logic, you start to lose your performance. So what is the solution? The solution is that you will devise your code, you will design your code in such a way that you can put all the logic in the same place in a single step. You should not really be afraid of a complex logic. Okay, because if you can put all the logic in the same place, then you are actually losing the performance in a single step. But if you break up that logic into 10 different steps, like if you in the where part, I can have a very complex logic where I need to call where 10 times. Okay, and somebody is clever enough, intelligent enough to combine all the logics into 1 or 2 steps. That means he actually gains a lot of performance compared to who uses 10 steps, because in each step you lose performance. So this is the only takeaway from here, that you so which is not good, I would say, which is not good, because usually we say don't be over smart. That means you keep your algorithm very simple. Okay, so that it's not only the computer which has to understand your logic. The logic part actually, the developer, your co-developer will have to understand. Okay, so this is one, to me, this is, I don't know exactly about others' opinion, this is one of the big drawback of NumPy, that you cannot really break your logic which selects your event into many different steps and think that somebody will optimize it away. But if you can put all the logic, or I mean at least relevant logic, in the same place, which can be done, then you can actually optimize your performance. Okay, so I go back to again this. So vectorization, I think you have understood, and how vectorization is achieved in. Yes, somebody's.
Yes, sir. I just have one question regarding the time it thing. Maybe not the NumPy thing, but the time it part. So, for example, right now here it's running the same cell 7 times and then giving us an average time for that particular run.
Yes, yes.
So, but if I just want a simple time for one cell run, is there a better way? Because I don't. If it's a bigger
So the
logic,
yeah,
yeah.
the better way is that let me find out one example. I think I have one example which I will find for you. So can you see my screen? This shell.
Yes, sir.
Okay, so you have a module called time. Okay, in Python. So here, this is also one example which I can share. Here you just benchmark different ways of looping. Okay, in this example, which I can run, and if I run it now, this one, you will see that my whole machine actually gets stuck. So I have to, if I want to run it, I have to reduce the number of elements. What I do, I have import time. So I'm importing the time module. I have one function sitting here, which is a very basic for loop, which you can see from that. I have another for loop which is through the list comprehension. Okay. Then you have the driver code. How do you do that? You say begin, and time.time. So it will give the beginning time. Okay, I will run it, and then you call the basic for loop 10 to the 8. Okay, so let us make a small number, not 10 to the 8, will actually, well, 10 to the 4, let us say. Okay, and then you say end time, and after this, both all these three lines are executed, you say time taken by for loop is n minus begin, and there is a way, because you have to check how it is done. You can just print begin and end, and similarly you can again do begin. That means you want to do something more. Okay, and you do this, and you say end time, and you print time taken by list comprehension is this. So does that answer your question? That if here you are only executing it once, the time statement.
Yes, it does. And so we have to explicitly do that
Yeah,
time
you have to
computation
explicitly
ourselves,
do.
right?
Yeah,
Okay.
I
No
don't
inbuilt
know.
function.
I don't know about other modules. I
Mhm.
don't know about other modules which you can use on the, because also some people say that there is a time module. That means instead of percentage time, you can also use time it. You can say time, but I have never used that. So anyhow, so I will just, because I'm telling you this, I should also run it. Okay, if I run it, okay, it doesn't take any time at all, so I have to increase it a little bit, but not much. You see that it takes some time in terms of seconds, I think. So up to 6 I can run. You see that I told you the very first day that list comprehension is might be more optimized than the original for loop, but it doesn't show that. it doesn't show that. But as you grow your array, maybe, so from 6, if I do 7, and I hope it will still return, it will not get stuck somewhere. And you see that now with another order of magnitude higher. And you see that there is a slight difference from the manual for loop to list comprehension. Okay, from 3.53 seconds to 3.26 seconds. Okay, so this is also something that I wanted to
Yeah,
show.
I think you said it correct. The time instead of time it will work for one loop, I guess.
Yeah, I
The
think so.
time magic
I
command.
read somewhere, but because I am used to time it, I usually use time it, and I mean, you have a more reliable representation of the number. And I think the time module is the one which I am showing here.
True.
Okay.
Thank you.
Okay, so let me go back to the slides because I have few more things to. I mean, there are many slides. I cannot really show you all these slides. I don't also have the time, but I only want to give you a flavor of how it should work. So, how do you create a NumPy array? A NumPy array can be created from scratch, but what you usually do is you take a list, Python list, and pass it to somewhere, which will create a NumPy array, equivalent NumPy array for you. So for example, this example, here what you are doing is you have np, which is my module, dot array. This is the function array, and you are passing two, so two lists. So this one list is 1, 2, 3, the other list is 4, 5, 6, and it is already annotated that the first list will be your first row of the NumPy array, because this will be a matrix at the end, and the second list will be the second row. So you'll have, if I really look at it, my NumPy array, which is the return one, ARR, will be a two-dimensional array or a matrix with 2 rows and 3 columns. Okay, this is something which is understood. So you can do that now. A few example I can execute. For example, I have already this one. So let us go to here. I already have something. So this one. So NumPy, import NumPy as np. Then you are creating that array. So let us enter. Okay, so you have created an array. Now you want to look at the type of the array. What kind of array it is? So let's do it, and you see that this has the nd array is the data type. So let us, instead of doing this, let us say print to explicitly print it. So the class numpy.nd array. So this is important. You have to check that it's an n-dimensional array, nd array, and this is the name of the NumPy array class. Okay. So what is the dimension? What is the dimension of the array? Okay. So so you can, there is an element. There is it's not a function. It's just a variable which is called ndim. Ndim will tell you what is the dimension of the array. Okay. If you want to know the shape of the matrix, in this case it's because two-dimensional, you have another variable, another member variable called shape. You can just execute it and it will tell you there are two rows and 3 columns. So this is the shape, and this is very, very important. And this shape, if you look at the type of shape, also that is important, because sometimes you may have to use that shape. You see that this is a tuple. So if you look at the shape, the value which is returned is a tuple. You can also look at the size. The size will be the total size of the array. Not if it's a matrix, it will be flattened and it will give you the size. Okay, so it will give you the size. Then by default, if you don't specify anything, it will try to infer the size of not the size, the type of the data that the array contains. For example, I have not specified anything. So it becomes the dtype. So dtype is another variable, will be integer 64. So it's a long integer. So all these things are there. Now, if, as I said, it is, if you already know that I am going to use only decimal point number, it is good to actually specify that from the very beginning so that Python can optimize it. Now, again, if you ask me about optimization, I will simply say that optimization will be that Python will immediately know out of n number of C functions, which it doesn't have to call at all. It only have to call a subset of all the functionalities. So that is kind of the optimization we are talking about when you specify the data type, because when you specify the data type, then and Python calls the C function will have all kinds of data type with which you can call the function. Maybe with different, with in C++ you have overloading of function, but in C you don't have function overloading. So you will have different names of the function for different data types. So if I specify the data type in the NumPy array, then immediately Python will know that those data types I don't have to call, because I am dealing with only some data type. So those functions which I am calling will be shorter, the list of functions will be shorter, and that will be my optimization, okay, in the memory space. So now if you have another array, array 1, and now look at the D type, and you see that because I already specified the F, and it tells me that I am dealing with floating point number, even if the value which I am specifying are the same. Okay, the value which I am specifying are the same. That means they are integer value. So, but Python doesn't infer the data type from the value anymore, because I have already explicitly done that. Okay, so this is another point. Now, if you want to print your array, you can print it. You can print it like this, and it will print that there are 2 rows and 3 columns, and it tells you that this is a matrix. You want to access some element, and Python will zero base. So if I want to access the element which is the second element from the first row, okay, and the second, so this one 1, so that means 1 from here and 1 from here. So it will be 5, like here. Okay, in the case of dimension, row and column dimension. And there is also this interesting one, that if you put array 1, and for the second one you have 1 then colon, that means now you are actually slicing the original array, and you are getting the first element, which is the row index, the second element, second row, and the full column, second row and the full column, because here you are putting a colon, means from the first, no, sorry, not the first, because you have put 1 from the second element up to the end. So this one is second row, and second column onwards, something like this. So if I execute it, you see that you get now an array, and this array is the second row, and the column starts from 1, and goes up to the end because of the colon. So this is how you actually access the NumPy array. It's not very difficult, but you have to get used to it. Okay, also I have issues. I mean, when I discuss, sometimes I miss the point. If you have, similarly, if you put 1, that means you are similar to this, and you have -2 and then colon, and -2, if you start, actually you are counting from the end. So -2 will be, because this is my second row, -2 will be -1 -2. Okay, so -2 will be like this, and it will be up to the end, because if -2 and colon something, so it will be again the same, 5 and 6. Of course, in these 2 cases you will prefer this one, because it looks much better. Okay, so then you can also another interesting thing is that you can have another matrix. In this case, you have 3 arrays, 2 columns. So let us do it, and I can insert one cell, and I can say m dot shape. So you have 3 rows and 2 columns, and now you can extract something. For example, what I'm doing is that I'm saying m1 colon comma 0. That means I'm talking about the first column, which is the first column. which is the first column, and I am going from the in the first row. In the first row, I am taking the first column is what? No, sorry, I'm not. First column will be this. First column will be this. I'm taking. Let's start from the. So I am taking the row number one. Row number one is this. Row number one is this. Up to the end, and comma 0. Okay, so let us first type print that and then look at. So first of all, let me. So 1 colon. So as I said, I also get confused. I can do that. So this one will give me. This one will give me 3 and 5. 3 and 5 because I am starting from row number 1. So row number 1 is not row number 1. Row 1 means 2, the second row, and I'm going up to the end. So both second and third row. And for the second and third row, I am picking up the 0th column, the first column. So which will be 3 and 5. So that's what I am saying, 3 and 5. And you see that it has, from a matrix, you have now got an array. Okay, and if you look at the shape of that, and you see that it has got 2 columns and there is only one. So just 2 columns if you think in terms of matrix. Okay, but we can always think in terms of a vector. Okay, so it doesn't have the second one. It will be 1. So if you think about it, it will be 1. So this is complicated. I agree that this is complicated. For example, this one is colon 2 comma 0. So from M, colon 2 comma 0. 0, if you think about it, 0 means the first column. So either this or this or this. And you are taking colon 2. That means you will go. You will. So there will be only one, because after that, I think you try to skip this one. Okay, I have to check that. This I have to check what it is. Okay, so before I do that, let me go to the slides again, because we have to explain this one. So what I say that ndarray, Python NumPy is an NumPy array is an ND array, and ND array has got some attributes which we have already seen without understanding much. So it has the ndim. Ndim is the number of dimensions of the array, which we have said. The shape of the array, which is the current dimensions of the array, because you can change the dimensions, which you will see soon. Then size, total number of elements in the array. Then dtype, the type of elements in the array. We have seen that also. Okay. Then item size in bytes of each element of the array. You can also check that. Okay. And data is the buffer containing the actual element of the array. That means this data will be close to the C array. Okay. So here you can see once more the same thing, that you have a NumPy, you have 3 lists, and from the 3 lists you have a NumPy array. If you print it, so if you print it, you get this 3-dimension this matrix with 3 rows and 5 columns. 3 rows and 5 columns. If you look at the dimension, it will give you 2. If you look at the shape, it will give you 3 and 5. It will look at the dtype. Okay, it will tell you that it's an integer. So dtype is also is an object, so you can also print the name of the dtype, data type. So in which case it will tell you a string. You can look at the item size. Item size is what? Size in bytes of each element of the array, because they are all long integers. They are 8 bytes. That's what it is telling you. If you print size, it will give you 15, 3 into 5. And of course, if you look at the type, then so this is a very important slide. Okay, this is a very important slide. All we have shown on the notebook are summarized here. Okay, and you should keep an eye on that. Okay, so now let's go to the other part. So these are the array access, and which I have shown there, and you can look at the link in order to do that. There are some cartoons to tell you how to access that. It's very difficult to explain on online, but I tried to do it. But the same thing The same things are here. So you can always check that. Okay, you can always check that. Now the important part. Now the important part, that because of the fact that we saw operator overloading, that in normal Python, if I want to check that one element is greater than 0, I would say if A is my list, then I will pass A within bracket. I will pass the index, and I will say greater than 0. Okay, but in the case of NumPy, if you want to check whether any element of a NumPy array is greater than 0, okay, you just say A greater than 0, then it will be vectorized way. It will be checked inside a inside a loop in the C world, not on the Python world. So that way, actually, you can, which we have seen in the case of where to some extent. Now we can see it more extensively. You can actually pass logic. You can actually pass logic where you will just specify the name of the NumPy array, and it will be vectorized, and the loop will be executed on C in order to give you the result. So, for example, let us first of all see one more thing: how you can create, not from a list, but from scratch, how you can create a NumPy array. Okay. So in the case of normal Python, you remember that you create a list by saying a range, no range, and if you pass 10 to a range, it will return you 0 to 9. In NumPy, you have a range. Okay, a range, this one. So np.arange is a function, and you put 1 to 13. Let's say I'll just copy this one on the terminal if it's not there. So I'll share this. Notebook after editing a little bit. So let us add here. So let me check this one. So np.arange 1 to 13. np.arange 1 to 13. So a equals to np.arange 1 to 13, and I also specify dtype because that is important here. Dtype is int 64. You can give anything that you wanted. Okay, so okay, you don't really need dtype. So np.int, this is just to tell you that you can do that, and that's it. That's it. So I can execute it. So A, if I print, I have an array. I have an array starting from 1 to 12. Okay. So this is slightly different. This is slightly different from the range, in which case you start from 1, but you end at 12. Okay, so it's slightly different. And these are types. So what you can do, because there are 12 elements, and this is a flat array, I can actually convert it into a matrix. That is important, because sometimes that is how you. So here, if I have A, I say shape. I say shape of A. I see that just 12. So what I can do, I can say reshape to, let's say 3 by 4, 3 and 4. And you see that now you have a matrix. Okay, so the reshape is a very, very important. Without changing the total size, of the array, you can actually change an array, a one-dimensional array, into a two-dimensional array or a three-dimensional array, etc. So that is very important, and that is done, you will see, almost ubiquitous. I mean, everywhere it's ubiquitous in machine learning. You reshape it almost every time. The fact is that if I do reshape of A and I print A again, and you see that the A doesn't change. So this is also very important. So reshape command is not an in-place command. It is just a view. So if I do b equals to a dot reshape 3 by 4. Then if I now print b, then I know that b is a changed array. So b was not there. Now b is an NumPy array, which is a matrix. So if I now look at the shape of b, I see that it's 3 by 4. Okay. So I think I have taken way too long than what I was supposed to take. So I will stop here. Okay. And if you have questions, I'll take that. Otherwise, in the afternoon, I will spend half an hour on some more things. Okay. Which, and then I mean, I will share the slides with all the details so that you can practice. You can. I will also share with you some old notebooks which I did last time. Okay. Also there I could not do complete anything, but I anyway shared all the notebooks so that you could practice. Okay. And then I think pandas will be impossible in the afternoon. We will only talk about, we'll only show some of the matplotlib examples, and we'll see whether we can do at least show one example with the pandas, because to me it was very important to tell you how NumPy works, why it is slow, what you can expect as performance, what you should, what are the recommended ways of using NumPy, and so on. The examples are important, but I think I have given you a very general but very simple overview, and in the afternoon we will show you how you can actually pass the whole NumPy array as a condition, as this slide is actually showing some condition, and get your work done. Okay, which is actually the realm of pandas. So I stop here because I think it's already more than 1 hour and a half. So if you have any questions, I will answer. Otherwise, we'll see you in the afternoon. I don't see anybody writing on the chat, so I think it's still fine.
Hello, sir. Can you hear me?
Yes, I can.
So, sir, we were just now looking at the example of arrange and reshape. So, we could clearly see that when we go from arrange to reshape, so it maintains the order or the index of the elements. So, let's say we want to arrange the 12 elements to 3 by 4, so it maintained the order. But let's say if we want to switch some element from one position to another, so I guess there might be some other functions to do that. I mean, there must be something to do that. Because let's say we want to go from arrange to reshape, but we want to switch some positions. So is there something, or maybe we have to make
To
some
be,
matrix operations on that?
yeah, I think so, because this is mostly geared, NumPy is mostly geared towards like algebraic operation. So once you reshape it into a matrix, now you can do a transpose, you can do all inverse and so on. So it is, you are not really, I mean, I don't know. As I said, I have to find out. There are 500 functions and I don't know all of them. So if you really want to arbitrarily change position at that point in the reshape part, okay, it might not be very easy. If you really want to change the position, then you should, after you reshape and you save it into a matrix, maybe you know what you want. So if transpose is good enough, you just do a transpose. If transpose is not good enough, you can do a reflection of the position. If you think that it should be a triangular matrix, you can somehow make one part of the triangle and just the other one. If you want to keep only, so there are examples. If you only want to keep the diagonal elements, you can do that, and so on. Okay, but arbitrary positioning, I don't know, to be honest. I have to find out. I'll check that. Okay, if I understood your question, that when you
Yes, yes.
reshape,
Okay.
whether you can arbitrarily change the indices, I have to find that out, because I have never used that use case at all.
Okay. Okay. Thank you.
Any other questions? Or, I mean, up to now, I have not asked whether you have followed it, but today, because it's a much more complex concept with NumPy, and practice will make you perfect, as they say. But you should at least have an idea about all the operations. So I'll share the slides if you, and also the notebooks, previous notebooks. So you should really, before your machine learning courses start, you should practice all of them seriously, so that when they talk about all the weights and the inputs and the biases, etc., and show you some probably because somebody if the first few lectures will be on machine learning, will also be elementary machine learning. So there, if they show you how to develop a network from scratch, then all the NumPy will come with its full glory. Okay, like what we are discussing here. So reshaping, then multiplying a matrix with an array, which is the weight versus the input, and so on. So all these things you should have a good grasp about before you move to the machine learning. So you have a few days. I will share everything today after we end the next session, and I think you will have enough time to practice all this. But in order to do that, I thought it will be good if you understand the basics. Okay? And then it's a matter of practice only. Okay, good. Thank you very much. This is a complex subject to discuss, but I hope I have conveyed a little bit to you. So I will stop here. I'll stop recording, and I'll stop here, and we'll see in the afternoon at 4 o'clock once more.